you can kind of have to like reason your way through that one. We only have a couple of minutes, so we'll just keep working the problems. I won't make you do them on your own and then go over them. We'll just work a few more until we run out of time. So, all right, let's see. Number 11 says the graph of a function f is shown above, which could be the graph of the derivative of f. So I made this little chart for John earlier today, and it might help some of you too. So if you are wanting to go between function and derivative graphs, everything moves down one every time you take a derivative. So when I look at a function graph, y values are y values, slopes are slope, concavity is concavity. Everything is as it should be when I'm looking at my function graph. But when you're looking at a derivative graph, the y values on a derivative graph are the slopes of your function, and the slopes of the derivative graph are the concavity of your function. So it moves down one when you take the derivative. And then it moves down again if you take another derivative. So the y values on a second derivative are the concavity of your function. So what they're asking us to do on this one is figure out how can I take the graph of this function and make the graph of the derivative. Well, the slope of the original function is the y value on the derivative graph. So I would look at the slopes of f to make the y value derivative. Right, so if I look at this original graph here, this is the graph of f. Its slopes will become the y values on my graph. So I'm looking for a graph that has positive y values from about here on the x-axis to here, and then has negative y values in between those two. The slope on f becomes y on the derivative. So we want positive y values, negative y values, positive y values. It would be b. If you look at b, it has positive y values in the same places that this graph has positive slope. And it has negative y values in the same place that this graph has negative slope. All right, number 12, we're taking a derivative of a power of e. So remember your rule for taking a derivative of a power of e. So in the last things we learned, it's that power of e times the derivative of power. So to take the derivative of e to the 2x, I'm going to write it 2 over x, sorry. I'm going to write it as e to the 2x to the negative 1. All right, so instead of 2 over x, I'm going to write 2x to the negative 1. So the derivative would be e to the 2x to the negative 1 times the derivative of of 2x to the negative 1. Why is it negative? Because you bring the exponent down to the front end. Oh, yeah. Yeah. Yeah, so that's one because you're doing a derivative. So this is the same as negative 2 over x squared times e to the 2 over x. Alright, number 13. I just wrote this weird. It's a chain rule problem. I just wrote it weird. F of x is x squared plus 2x. Then the derivative of f of ln x. So they're saying if natural log of x is inside of the f function, then what would the derivative be? So we have to take the derivative of the outside function, which is f. So that would be 2x plus 2. Alright, so 2x plus 2. But instead of x, we're going to keep the inside function here, because they're saying plug natural log of x into the f function. So we would do the derivative of the outside, 2x plus 2, leave the inside alone, times the derivative of the inside. So the derivative of the natural log of x, the derivative of a natural log, just u prime over u. So we would just do the derivative of x over x. 2 ln x plus 2 over x. So the derivative of the outside function, that's the f function, is 2x plus 2, but our inside is going to be what's inside of 2x plus 2 instead of x is going to be ln x. And then the derivative of ln x, which is the outside function and the inside function, until we get a. Alright, I only have a couple more minutes, so let's look at number 14. The polynomial function f has selected values of its second derivative given in the table above. Which of the following statements must be true? There's a couple of them that could be, but there's only one that must be, which is what makes this one kind of tricky. So remember, what the second derivative tells you is it tells you about concavity and points of inflection. Right? That's what the second derivative tells you. So any other thing, increasing is the first derivative. Decreasing is the first derivative. Local max or min is the first derivative. Right? What we're going to look at are the two that talk about points of inflection, concavity. And this is where it gets tricky, because if you look at 1, the requirements for a point of inflection are that the second derivative equals 0 or be defined and change sign. And it looks like that happens there. Right? If I look at 1, it is equal to 0, and it does appear to change signs. To the left of 1 it says 5, and to the right of 1 it says -7, so it goes from positive to negative. The problem is that there's a whole lot of other numbers between 0 and 1. So at some point between 0 and 1, it could have gone negative and then back up to 0, because it doesn't tell us this is the only 0 for the second derivative. It's just picked some values. So it could have gone from positive 5 to negative something between 0 and 1. And so if between 0 and 1 it goes negative, then it doesn't change signs at 1. Or you could say the same thing between 1 and 2. It could have gone from 0 to some positive number before it came back down to -7. So there could be a point of inflection at 1, but there doesn't have to be. The only thing that has to happen is somewhere between 0 and 2, your second derivative goes from a positive to a negative, so it has to change concavity somewhere in there. Right? Concavity changes if the second derivative changes sign. But you could at least narrow it down to 2 of them if you knew that the second derivative determines concavity and points of inflection. The first derivative determines increasing, decreasing, and maxes and mins. Alright, it's 4 o'clock, so no, I'm going to stay after school tomorrow on Wednesday. Okay. So if you want to stay, you're welcome to stay, and I'll work some more problems, answer questions, that kind of stuff. So, get some last book cramming in.